Every day, the future's getting closer.
Welcome to Master the NEC, where we talk about the National Electrical Code and all things electrically related. My name is Paul Abernathy, your host, and welcome to today's podcast. Well, hello everybody. Welcome to another episode of Master the NEC, where we talk about the National Electrical Code and all things electrically related. My name is Paul Abernathy, your host as always, and welcome to our podcast. I also want to remind you that you can also listen to Master the NEC podcast on your Alexa devices like the Echo Spot and the Echo Dot. All you got to do is go to your Alexa app on your phone, go to the area where you add skills, search for Master the NEC podcast, all separate words, and you'll see it. You add it. It will add it to your daily briefings, and all you got to do is say, Alexa, what is my daily flash briefing? And, of course, you can add us. We'll be in there, and you can listen to all of our most current podcasts right there on your Alexa devices. Okay, so today's episode, we are going to talk about something that sometimes adds confusion, not just for home inspectors, and we've done a podcast and a video on that, but sometimes electricians also will get confused at the understanding of, I have conductors, and my conductors are rated for 20 amperes, 30 amperes, 15 amperes, and then I have to protect them at that ampere rating based on 240.4. And if it's small conductors like that, 14, 12, 10, then they usually will refer to 240.4D, which is titled small conductors. And that is true. The general rule is you protect a conductor at its ampacity. And so based on this, if you look at 240.4D and you go down, you have 1, 2, 3, 4, 5, 6, and 7 options under D. You'll see that it says, for example, a 14 gauge copper is protected at 15 amperes. So, that's what you do. And we're all very used to that. But you'll also notice that it also states in there that it can be permitted to not be protected at its ampacity, theoretically, by the allowances of 240.4G and E. And so that's what the topic of today's episode is. We're going to talk a little bit about that because I want to remove the confusion that people have about how to apply the applications in G. So, if you've got your code book, we're in the 2017 National Electrical Code. You go to 240.4D, you see small conductors. And then again, it says, unless specifically permitted in 240.4E or G. And of course, when we get to G, you'll see that it is specifically permitted for what our application is that we're going to talk about, which is an outside air conditioning unit. Very much applicable also to motors as well because of the inrush. Remember, the conductor can handle the running current, but you also know that there's inrush current that could come in. But we'll talk. We discussed that in our motor video. So if you haven't watched our motor video, go watch that on our YouTube channel. You can get there by going to masterthenec.com. Up at the top, you'll see a button that says "Watch our YouTube videos." Click on that, and you can get to our YouTube channel. All right, so let's talk about small conductors. Now, actually, you can see that D1 through D7 deals with 18 gauge, 16 gauge. I'll remind you, neither one of those can be used in a house or installation. The smallest allowed is 14 gauge. But there are other applications where 18 and 16 throughout the NEC can come into play, certain applications. Okay, so it's in here. But what gets us usually for people is that you'll see that D3, for example, will say 14 AWG copper is good for 15 amperes. And you'll notice that 12 AWG aluminum or copper-clad aluminum, which is basically just aluminum with a copper veneer, if you will, is good for 15 amperes as well. And, of course, you see 12 AWG copper is good for 20. And so you run into that there. Now, you notice up at the statement where it says, and I'll read it because it's dealing with small conductors, and that's kind of where we want to base today's episode and more gear it towards HVAC unit applications because there is still confusion in why can I put a 14 gauge copper and terminate it on a 30 amp or even a 40 amp overcurrent protective device. And so we're going to kind of talk about that in this episode. Now, small conductors, here's what it says. Now, if you're following along in your code book, it's on page 94. but it's under 240.4D is where we're reading. And it says small conductors. It says unless specifically permitted in 240.4E or G, okay, it says the overcurrent protection shall not exceed that required by D1 through D7. Now that is the protection for the conductor matching the overcurrent device that's protecting it, okay? And it reminds you that this is to take place after correction factors have been applied. Okay, so you might have to use a 90-degree value for an adjustment and correction, provided that the insulation is rated for 90. Remembering that you do have terminal limitations in 110.14c. If you don't know what terminal limitations are in sizing conductors and adjustment and corrections, then you need to go watch our video called Derating Demystified. So go to our YouTube channel. You can find it. It's about 2 hours long, but I will walk you through the whole process of how to apply adjustment and corrections in 31015 B2A and 3A of the National Electrical Code to help you get a better understanding of that. So if you haven't done that, go back and watch that video. All right, so in our case, we're looking at G. And the reason I say that is specifically permitted. People get confused with that as well. Just had a recent thread. Also, I should do a shout out. If you are trying to study for your exam, or you really want to surround yourself with other people that are preparing for an exam, whether it's your engineering or electrical or inspector, then you might want to go to our Facebook group. And in our Facebook group, search for Master the NEC Exam Prep. And you will see that that's a closed group. If you answer the questions and you want to get in the group, do so. Remember to answer those questions, otherwise you're liable to get rejected, because we're really asking you, are you here to prepare for an exam? And that's the people we want in the group. If you don't, you just want to go to our Master the NEC page, that's fine. Both are on Facebook. Again, search for Master the NEC Exam Prep and Master the NEC. We have 2 different forums on there. Master the NEC is open to everybody, and Master the NEC Exam Prep is only open to those who are interested in learning more about the NEC when it comes to exam prep or licensing stuff. That's where you'd go. Okay, so small conductors, we're going to see specifically permitted. Now we're dealing with, let's say, an outside air conditioning unit. Okay, and it has when we're dealing with that, it has a unit on it, and it has everything. So that's what we're dealing with. So if you go over here, and we're going to just deal with the conductors today, but I'll briefly talk about the overcurrent device. When you see a nameplate, for example, on the side of an air conditioning unit, it'll have a minimum circuit ampacity and maximum overcurrent protection. And it'll all be marked on there. And it's all based on the manufacturers doing their testing, but it also comes from a specific parts of the National Electrical Code as well, so you kind of get an understanding of how they came out with that. Now, what parts are those? Since we're dealing with air conditioning unit, we're dealing with 440. It's Article 440. And Part 3 and Part 4 is the genesis for those nameplates, so where the manufacturer comes up with those nameplates. And, of course, they test them, and that's what they're able to put on there, and we'll talk about that. Okay, so let's do a scenario. What if you come across and you're sitting there and you see a nameplate that says minimum circuit ampacity of 18 amps, maximum overcurrent protection of 40 amps, and you're sitting there going, there's no way that I'm going to choose, for example, a 12 conductor for 20 amps, and here I am in a situation where I am going to potentially protect that with a 40 amp breaker. And you're like, this just doesn't sound right, because right here in 240.4D, it says that a 12 gauge has to be protected with a 20 amp overcurrent device. I mean, that's what it says. But again, it tells you specifically permitted. In our case, we're dealing with an air conditioner. It could as well be a motor, and you see that in the list as well. And there's a bunch of other things in the list as well, like electric welder circuit conductors, capacitor circuit conductors. But today we're going to deal with the air conditioning and refrigeration equipment circuit conductors, and we're dealing in 440, and most notably an outside air conditioning unit. Okay, and so we're going to be looking at the overcurrent device requirements in Part 3 of 440, and we're going to look at the circuit conductor rules in Part 4 of 440, which are going to change the rules that are here in 240.4D because of that specifically permitted use of 240.4G. Now, a lot of people get confused when it says specifically permitted. They think it needs to, when you get to Part 3 or Part 4, that it's going to make some reference back to 240.4D, and it's really not. You know, the rules in 240.4D for small conductors are stated pretty clearly. But it's moving you out of that. It's saying, okay, this is the general, but you can go on and do what it says in 240.4G, and by virtue of that, in 440 Part 3 or Part 4, we're okay with it, okay? We'll let you do that. And that's the specific permission that it's giving, okay? A lot of times, people will want to see the reference back when you get to the Part 3 or Part 4. In some places in the code, it will do that. But in other places, it's just not. It's saying, look, you're here now, and you're doing it. Okay? And so keeping that in mind, we're now going to go to 440 Part 3. That's where we're going to go. So if you got your code book, you're going to go to that. I will give you the page. It makes it a little easier for you if you're just flipping along. And Part 3 is going to be on page 326. At least that's where it starts. Okay? And I'm in the 2017 version of the National Electrical Code. All right? Now, let's read the general rule because we're going to start talking about the branch circuit, short circuit, and ground fault protection. So if you're thinking about the nameplate this time and you see this on the side of the unit, this is good information to know because there might be a case where you don't have a nameplate or it's worn off or it's fell off or something's happened and you need to know where they got their values and maybe the conductors are existing and you want to try to do a reverse engineer it and you want to see what's being done, then this is important to you. But again, I remind you in all normal cases, new construction, you're going to have a nameplate. Don't overthink this. Follow what the nameplate says and you don't have to worry about it. But inquiring minds always want to dabble and learn. Apprentices, journeymen, masters that are learning. It's probably funny because the apprentice wants to really learn. The journeyman's like, yeah, I want to learn. The master's like, just do the nameplate. I got time. I don't have the time for this. And I get it. And then there's some masters that really do want to learn it, or maybe they've already learned it through their experience and whatnot. So let's read to 440.21, the general. So we always want to read the general statement so we can know where we're coming from. So it says, the provisions of Part 3 specify devices intended to protect the branch circuit conductors, the control apparatus, and motors in circuits supplying hermetic refrigerant motor compressors against overcurrent due to short circuits and ground faults. Okay? They are in addition to or amendatory of the provisions of Article 240. So there's your permission. Okay? It is in addition to or amendatory, okay, to the general provisions of 240. And of course, we were just talking about the applications in 240.4, for example. So we're kind of getting that permission right here. Okay. So and you'll see a very similar language, similar, I should say, for the general in Part 4. But we're talking about Part 3. So let's kind of look at it. Now, a couple things. 440.22 is the application and selection. So in our case, if we have an individual motor compressor, and in our case, most of those HVAC units, that's what you're going to deal with. If commercial application, it might be more intense than that because you might have multiple units being fed by one branch circuit. Okay, but in our case, we're just going to keep it very basic for this episode. We might have an advanced episode where we do some more, but I'm going to keep it very basic because I think you just need to understand the concepts of these nameplates and how they come about. All right, so the first one says rating or setting for individual motor compressor. So it says the motor compressor, branch circuit, short circuit, and ground fault protective device shall be capable of carrying the starting current of the motor. It says a protected device having a rating or setting not exceeding 175% of the motor compressor's rated load current or branch circuit selected current, whichever is greater, shall be permitted, okay, provided that where the protection specified is not sufficient to start the current of the motor, the rating or setting shall be permitted to be increased but not exceed 225% of the motor's rated load current or branch circuit selected current, whichever is greater. Let's keep it simple. We're going to talk about the motors. Okay, we're going to really keep it to the motor compressor's rated load current of that motor because you're trying to either use a nameplate or calculate this yourself. Now, example, We're going to size the conductors. That's a given. But when it comes to doing the overcurrent device, you might put something on it, and it might not handle the startup, the inrush of the motor. Okay, now if that's the case, then you're allowed to exceed that 175%, but you can't exceed 225%. So the rule here is to allow you to protect it up to 175% of the motor compressor's rated load current. Okay, now that is generally going to be what you're going to run into as your first step. Only when it is not sufficient, or that 175 device that you've selected can't handle that sudden inrush, then what happens is you can go up to 225%, but you can't exceed it. Now, the manufacturers do this on their nameplate. They test their motors. They test their equipment. When they produce a nameplate, they have already given this information into consideration. So when it says the maximum overcurrent protection, then they've already taken this into consideration. Okay. Now, if you're doing it without that and you're dealing with something, you might try 175% and it for some reason trips out, it won't hold it. Then you can obviously swap that out and go up to 225% because you have physically done this test to do that. But most of the time, again, follow the nameplate. You're good to go. All right. So that is for A. Then you get to B. Now, again, A might be the most cases what you're dealing with because most of the time we're running to an individual motor compressor that's inside one unit and we're done when it comes to that. And that's they're doing the nameplate. But let's look here. When you can get out of that scenario is when you get into B. Now, what does B say? Now, B says rating or setting for equipment. Okay, now it says the equipment branch circuit, short circuit, and ground fault protected device shall be capable of carrying the starting current of the equipment. Okay, it says where the hermetic refrigerant motor compressor is the only load on the circuit. Okay, it says where it's the only load on the circuit, the protection shall comply with 440.22a. Again, if it's the only load and it's the only motor and it's the only unit, then theoretically it's the only individual motor compressor. Now again, A was dealing with the motor compressor. B is dealing with the whole concept of the whole a piece of equipment. Okay, so we're dealing with that type of application. All right. Now it says where the equipment incorporates more than one hermetic refrigerant motor compressor or a hermetic refrigerant motor compressor and other motors or other loads. It says the equipment, short circuit, and ground fault protection shall comply with 430.53 and 440.22 B1 and B2. So there is occasion where you're not just supplying an individual motor compressor. You might be able to be supplying a piece of equipment, okay, whether it's a branch circuit or feeder, that you're supplying that actually has more than one load in it. It might have the hermetic refrigerant motor compressor, and it might have another motor load like the fan load or something in it. And that's taken into account on the manufacturer's nameplate as well. Okay? So that's the type of things that they take into consideration. Now, under 440.22 B1 and B2, it's giving you guidance on how to determine this. Okay? For example, B1 says motor compressor's largest load. It says where the hermetic refrigerant motor compressor is the largest load connected to the circuit. Okay, you might have other motors, but that is the largest load. It says the rating or setting of the branch circuit, short circuit, ground fault protected device, that's back there on the whatever's feeding that circuit, shall not exceed the values specified in 440.22a for the largest motor compressor plus the sum of the rated load current or branch circuit selected current, whichever is greater, of the other motor compressors and the ratings of the other loads supplied. So you take the largest motor compressor, refrigerant motor compressor, and then you take the RLC or rated load current of the other motors or even the other smaller compressors that might be applicable to that piece of equipment. Okay, and that's how you're going to derive it. Now, you have B2, which says, okay, what if that motor compressor's not the largest load? Okay, well, it's going to give you some guidance here. It says where the hermetic refrigerant motor compressor is not the largest load connected to the circuit, might be pretty rare, but I'm not, I'm just going to state that. Most of the time, the hermetic motor compressor is larger than the other components that would be in there. But just in case, the code gives you rules on this, guidance. And it says, the rating or setting of the branch circuit, short circuit, and ground fault protection device shall not exceed a value equal to the sum, okay, sum meaning adding them up, of the rated load current or branch circuit selection current, whichever is greater ratings, for the motor compressors, so you add them up, plus the value specified in 430.53 C4, where other motor loads are supplied, okay? And then it says, or the value specified in 240.4, where only non-motor loads are specified in addition to motor compressors. Okay, so what I want to do is say, okay, you're taking the sum of all the compressors, okay, and they're not the largest load, plus you got to add the value that's specified in 430.53 C4, okay? So what is that? Okay, C4 is, it says the branch circuit shall be protected by fuses or inverse time circuit breaker having a rating not exceeding that specified in 430.52. And you remember, for example, that is inverse time is 250%. So you have all those values. Again, you have a non-time delay is 300%, all those type of things. So when you're dealing with fuses. So that's that table that we're familiar with in 430.52 for the maximum rating or setting of motor branch circuit, short circuit, and ground fault protection. So that's what it's alluding to, okay? And it says that for the highest rated motor connected to the branch circuit plus an amount equal to the sum of the full load current rating of all other motors and the ratings of other loads connected to the circuit, okay? So it's kind of giving you all this information about how you do it. It's not overly complicated, but you just need to understand how they achieve that. And that is very difficult unless you're buying a package where you have other motors and other compressors and other things together, say in a commercial application. Then if that's the case, then you're going to have to do a little math. Or if you buy a package, maybe they provide that for you. If it's a total assembly of multiple HVAC units all coupled. But most cases for me and you, we're probably going to deal with the rating and setting for the individual motor compressor. And then, of course, that's where you get it. So just so you know, 440.22, when it comes to the overcurrent protection, which is really achieving the short circuit and ground fault protection as well, all of that comes from this area of the code. Okay? Now, the other thing that we have to really take into consideration, and we'll talk about it a little more, obviously, when we get to the conductors, is that you have to understand that motor branch circuit conductors, they're going to be sized in 440.33, and when we get that. But since overload protection may permit a motor to run continuously overloaded, again, up to 140% of the full current, that's built into the code. That's allowing that we have to be able to handle that overload. And so, again, we have to look at how that works out. And by using our calculations, and we're assuming the largest motor of a group, if we're doing a group application, this is automatically building in that extra capacity it's provided. And it will normally be enough to handle any foreseen overloads on the smaller motors involved. And it'll have enough diversity involved in that for the existence of any normal groups of motors that might have an overload condition, but it's well within its specifications. Okay, so that's the things that we all take into account when we're sizing these things out. But again, keeping it simple for me and you, if we're dealing with an individual motor compressor, we have that 175. If it doesn't hold, we have that 225. That's where most of those single air conditioning units for dwelling units, apartment complexes, where each unit is separate, that's where your nameplate's generally coming from. Now, if you have other equipment that incorporates the hermetic refrigerant motor compressor and other loads in there, okay, then that is where you're going to get into the allowances of 440.22 B1 and 2 that you have to take into consideration. And again, most of the manufacturers will actually go with the motor compressor as the actual largest load, and they'll use B1, and they'll derive their nameplate off that. And of course, that is usually going to bring us back to the values that are in 440.22a, plus they're going to add the sum of the rated load current of the other motors that are associated in that equipment. And that's generally what they're going to use. So it's generally going to be 440.22a or B1. That's generally. Again, remembering now, if the motor compressor is not the largest load and there are other larger loads in there, then you got to look at B2 in case you're doing that. Okay. All right. So we'll kind of keep it there for that, so we don't lose sight of what it is. Except for I will make one last statement in 440.22c. It says protect the device ratings not to exceed the manufacturer's values. So again, they're giving you the values. It says where maximum protection device ratings are shown on a manufacturer's overload relay table for use with a motor controller are less than the ratings or settings in accordance with 440.22a and b for whatever reason. Remember, if that's the case and the manufacturer provides you, it says the protected device's ratings shall not exceed the manufacturer's values marked on the equipment. Okay? So, ultimately, it rounds back around. When you see the nameplate, you see the information they provide you, follow the nameplate. Okay? Now, let's move on to part 4, branch circuit conductors. I'm going to read you this here. It says 440.31, general rule again. It says the provisions of part 4 and Article 310, which is dealing with, again, our ampacity values are all in Article 310, of conductors required to carry a motor's current without overheating under the conditions specified, except as modified in 440.6a, exception number 1. Okay? Another thing will remind you that the provisions of this article shall not apply to integral conductors of motors, to motor controllers and the like, or to conductors that form an integral part of an approved equipment. Look, don't over-engineer something. We're talking about the branch circuits that's feeding the equipment. We're not talking about the actual wiring that's involved inside of actual approved equipment. If it's already approved, it's listed, and it's installed, there's no sense in digging into the wheels. I don't want inspectors coming out there and going overzealous and say, well, this is what the size of the conductor has to be to your piece of equipment. But now when I look at inside your piece of equipment, these conductors look undersized. That's not the intent here, okay? So keeping that in mind. Now, let's talk about a single motor compressor. So again, we're going to fall back to our single air conditioning unit with a single motor compressor, and we're going to talk about sizing those conductors. Now, branch circuit conductors supplying a single motor compressor have to have an ampacity that is not less than 125% of either the motor's compressor rated load current or the branch circuit selection current, whichever is greater. Now, most time, we're going to simply do it by the motor's compressor rated load current, and that is what the manufacturer is going to do as well, because they're the ones that know what their motor compressor rated current is. And so they have done that, and that's what they've applied, and they're coming up with the minimum circuit ampacity, and that's what's on there. All right? So that's what we're falling in, and that's what we're going to do just for today's episode to keep it simple. That's what they're dealing with. Now, what happens if I'm dealing with, and that one's pretty simple because you wonder where they come with the values. And in your mind, you're thinking, well, how in the world now can I have a 14-gauge conductor protected by a 30-amp overcurrent device? Well, if you followed along to this point, you notice that it said that it could go up to 175% for the overcurrent protection, or the protective device, I should say, for the branch circuit, short circuit, and ground fault protective device. I should keep saying that. It can be up to 175%, but if that doesn't hold, it can be up to 225%. Well, that's obviously larger, and that is also based on the rated load current. So how come the conductor, it says that it's based on 125%? So the logic would tell you that at the least, the short circuit ground fault protection device for the motor, for the HVAC unit, could be 50% larger than the value that you would get for the conductors, because that is a minimum of 175%. And of course, if that doesn't hold, then I can take that protected device up to 225% of the motor's rated load current. So as you can see, the conductors only have to be 125% of that rated load current. That's for inrush. Once it starts running, it will drop down and it still will be considered protected. Okay. The other thing to remember is that most of these motor applications also have an overload component in there as well. Okay, so keeping that in mind, there is the overload protection that is inherent as well. So not only you have the short circuit ground fault protection, but in most all cases you're going to have an actual overload protection as well, integral. All right, so we understand now for the single motor compressor, no problem, 125%. Now, what if we have motor compressor and it has additional motor loads in it? Well, if we have additional motor loads that are associated with it, then the conductor supply one or more motor compressors with or without additional motor loads. So we could have just additional motor compressors, okay? And we want to size those conductors to that as well. So here's what the code says. It says conductor supplying one or more motor compressors, okay? So that's, read it there, one or more, with or without additional motor loads, shall have an capacity not less than the sum of each of the following. Okay. So the first one is pretty clean cut. It really just tells us what we did in 440.32. If it was a single motor, it says the sum of the rated load or branch circuit selected current, whichever is greater, of all motor compressors. Well, if there's only one, then that's it. It also goes on to number 2, says the sum of the full load current rating of all other motors. So we're taking the motor compressors, and if we have other motors in there, then we're going to take the full load current. And of course, we know that that deals with the full load current, depending on the motor, whether it's single phase, 3-phase, or whatnot, that's in 430.250 or 249. And we're going to get those values for those motors. Okay. And in 3, it says 25% of the highest motor compressor or motor full load current in the group. Okay. So if it's being fed by the same conductors, branch circuit or whatnot, feeding it, then at that point, you got A, B, and C here in order to come up with what you need. And again, you're just simply looking. If it was only the one, then it's going to revert you back to the application that we did before. So if you're dealing with motor compressors, okay, then you got the application here where you're dealing with the sum of the rated load current or branch circuit, whichever is greater, the motor compressor, the sum of the full load current rating of all other motors, and then 25% of the highest motor compressor or motor full load current in the group. Okay? So you have the different applications. Now, again, for most applications that we deal in, you might just be dealing with a single motor compressor for that circuit, and it's 125% of the motor compressor's rated load current. Okay? But you do have to understand, you do have the application 440.33 with motor compressors with or without additional motor loads. Now let's go a little bit deeper with that, because most people are satisfied with the single motor compressor, the 125% of the motor compressor's rated load current. But in many cases, we have other applications or other low motor loads or additional motor loads that we have to deal with. So we'll kind of just talk a little bit about that. All right, so look. Really what we're dealing with is where more than one motor is connected to the same feeder or branch circuit. It doesn't matter. The calculation of the conductor size must provide ampere capacity at least equal to the sum, okay, the sum of the nameplate's rated load current, okay, and in this case, you use the higher of the values, whether it's the nameplate rated load current or the branch circuit selection currents, you're going to use the higher. And you're going to do plus 25% of the current, okay? Again, choosing whether or not you're using the nameplate rated load current or the branch circuit selected current. Most all cases, we're probably going to use the nameplate rated load current to do this, okay? And you're going to, so you want to add the plus 25% of the current, okay, of the largest motor in the group, all right? And that's what's going to give us an application on when we're dealing with motor compressors with or without additional motor loads, okay? So let's kind of give this into context. All right, first thing we want to remember that it's really important to keep in mind that when you're selecting the conductor sizes, the nameplate current rating of an air conditioning motor are not constant maximum values during the operation, okay? It fluctuates. Now, the ratings are established and tested under standard conditions of temperature and humidity. Now, operations under weather conditions more severe than those at which the ratings are established will result in a greater running current. So that's why we're doing a lot of these things, because there is times when that current's going to change, especially if we have multiple applications here. Okay. So keeping that all in perspective, since overload protection may permit motors to run, again, as I said earlier, continuously overloaded, again, in cases up to 140% of the full load, feeders, for example, must be sized to handle such of an overload. Okay, and you do this by basing the calculations on the largest motor of the group, and that's what we were talking about, taking the largest one in the group. The extra capacity that's built into that will typically be enough because that is the largest motor, and there's usually not all on at the same time. It builds in that diversity in that group of motors, that's why you choose the largest, and then you take the sum of the others. So that's how you actually build that into it, okay? So that's where they get that. Now, there are many applications, and I'll probably get into a lot more advanced applications, but just remember that the ampacity cannot be less than the sum of each of the following. And you have a 1, a 2, and a 3, and you simply follow them down the list, okay? You simply take the difference in the 2 is in 440.32a. You're simply taking the motor compressor's rated load current and at 125%. Okay, I mean, that's simple. When you're dealing with motor compressors, that multiples, let's say, with or without additional motor loads, then you come into this aspect and you go, well, if I've got conductors that are applying one or more motor loads with or without additional motor load, shall have the ampacity not less than the sum of each of the following. So the first one is you got to take the sum of the rated load or branch circuit current, whichever is greater, of all motor compressors. Okay, so I take that. Then I take the sum of the full load current rating of all other motors that might not be motor compressors. I get it. All right. And then the last one says 25% of the highest motor compressor or motor full load current in the group. So you're adding that additional 25% onto it. So if it was only, I'm going to kind of give you perspective. If it was only one motor and you take the full rated load in number 1, but there's no other motors like we looked at in 440.32, you still, it says take 25% of the highest rated motor compressor, which would be the sum plus 125%. That essentially equals what you did in 440.32 if there was only one single motor compressor. Okay, so 440.33 is just taking into account where you might have more than one. If you still only have one and you use 440.33, you're still going to come up with the same value at 125%. Okay, so again, it just makes it simple. Go to 440.33 if you have more than one or you have additional motor loads that are inside your application. Or if you have one single motor compressor, then you stay in 440.32. What I'm trying to say is that is how they come up with the minimum circuit ampacity, okay, and these values. So you're in 440.32 or you're in 440.33 if there's other additional motor loads that are associated, okay, with that motor compressor. And then the last one that we kind of just dabble in is 440.34, which is combination loads. And that can get slightly complicated if you want to make it complicated. But it says conductor supplying a motor compressor loads in addition to other loads as calculated from Article 220, because Article 220 is our calculation article, and other applicable articles shall have an ampacity sufficient for the other loads plus the required ampacity for the motor compressor loads determined in accordance with 440.33. Again, because 440.33 is dealing with motor compressors with additional loads, so it makes sense, right? And it just goes on and says, and or for a single motor compressor in accordance with 440.32. Again, so you have these other loads you have to calculate into it, whether or not you're dealing with a single motor compressor or you're dealing with the motor compressors or multiple motor compressors with multiple additional motor loads. You have to also, if it's a combination load, which also has these other loads that are added on it that are calculated from Article 220, that you're taking all of this into account, okay, when you're doing it. Now, there is an exception here that says where you have interlocking that prevents simultaneous operation of the motor compressor and the other loads that are connected, then the circuit conductor shall be determined from the largest size required for the motor compressor and other loads to be operated at that same given time. Okay, so that's what you're doing for your motor compressor. Okay, but you don't have to take into consideration all of these other combined loads if you're doing it for the motor compressor and other loads that are going to operate at the same time as that motor compressor, you don't have to take into account those other combined loads that will not operate at the exact same time. Okay, so what I wanted to do is give you an example, and hopefully I won't lose you with this example, is another combination load example under for 440.34. And this can be intense. So if you're ready to be confused and dazed, then here we go. We'll go into it. All right. Well, actually, you know what? 440.34, I really don't need to give an example of that one if you think about it. Now, 440.33, I'll give you an example. But 440.34 is basically saying, hey, do your calculations for under 440.33 or 440.32 for your motor compressor and associated loads. And just don't forget that if you have other loads that are calculated or associated in Article 220, then you have to take that into account and bring them together if you have a combination load. So conductor supplying a motor compressor load in addition to other loads is calculated from Article 220, and other applicable articles shall have an ampacity sufficient for the other loads, plus the required ampacity for the motor compressor load determined in accordance with 440.33 and 440.32. So if you have applications where you have it, you have to make sure that if you have combined loads and they're falling under something that would calculate in Article 220, that you need to take into account the loads here for your motor compressors and all that. In addition, you need to make sure you combine those. However, again, the exception says that where there's an interlock provided that one doesn't control the other. One example might be where heating and air conditioning, where the heating can't come on if the air conditioning's on, there's an interlock to keep those from two. Then that would be an example of something that prevents simultaneous operation. All right. I guess the one we want to give a real example to, because of the confusion, is 440.33, motor compressors with additional motor loads. Let's focus on that one, because that one's probably the one that's going to confuse people the most. Okay, so let's just kind of look at it here. Let's say we have a panel, 60 amp, a 6 gauge is feeding a disconnect. It's a 15 horsepower rated disconnect. And we have an air conditioner. In that air conditioner, there is a condenser fan, there is a compressor, and there is an evaporator fan. Okay, big air conditioning unit here. Okay. So what we've got is a 1.5 horsepower, 230 volt, 3-phase motor. That's the condenser fan. It's 6.0 amps full load, and it's 40 amps locked rotor. Okay, and we got all that information, obviously, by going in 430.250 if we're dealing for the 3-phase motor. Okay, the next one is the compressor. It's a 3-phase, 230 volt, 26 amp full load. And then it's 150 amp locked rotor, okay? For this one here, it's a 10 horsepower motor. And then the next one was an evaporator fan, and that was 1.5 horsepower at 230 volts, 3-phase. It's 6.0 amps full load, again, the same as the condenser fan. And then it's, again, also 40 amp locked rotor. Now, branch circuit conductors, all right? So we had a 60 amp panel. It's a 60 amp device. It's feeding 6 AWG, which is feeding a 15 horsepower disconnect. So it's horsepower rated disconnect. And then it goes in, and then of course, then it branches over to, let's say termination branches over to the starter for the motor. Okay. Each one of these have a starter, but it branches over and it's using 14 gauge. So kind of let's get an idea. So the branch circuit conductors that's supplying it, we determined the largest motor was 26 amperes. That was the compressor motor. So we took that 26 at 125% plus the 6 and the 6, which was the full load current on each one of these units here. We're not doing the locked rotor. We're doing the full load current. Okay, of these 1.5 horsepower, 3-phase, 230 volt. So that's 6. So you take the 26 amps full load current of the largest motor at 125% plus the 6. So that's 44.5 amperes, which would be fine for a 6 AWG. Now, what about the compressor conductors? No, that's the compressor. That's the largest. So that one was 125% of 26 amps, which is the full load current. And that equals 32.8 amperes. So that's an 8 gauge that's supplying that. Okay. So then we're talking about the fan conductors. All right. So in the fan conductor application, it's 125% times 6.0, because that's the full load current for the fan. Okay. And so that equals 7.5 amperes. All right. But 1/3 times 50 equals 16.7 amperes. Because again, in this application, just an easy way to say that obviously if it's 7.5 amps and we have to have a minimum conductor sizing is 14, so we're going to choose a 14 gauge wire to do that application. So we've done it that way. So it's a 14 gauge. It's running over to the fan conductors. And fuses, protection. Okay. What are we doing here? So it is, what did we say earlier? How we did that? Since we have multiples, it was the 26 amperes times 175%. Of course, in case it doesn't hold, but in this case, we don't know any difference, so we're doing it at 75. So the fuses would be 125% times 26 plus 6.0 plus 6.0, which is 57.5 amperes. So 60 amp fuses. So it is subject to the group fusing restrictions for starters. Okay, so the wire size is based on the limitations because of the size. You got to remember that 110.14C1A rules is going to keep you in the 60 degree C column for those conductor sizings. So, but we're dealing with fuses here. So it would be 60 amp fuses, but we have to remember the applications of the other fuses that are in the group. But in our case here, it would be a 60 amp feeding a disconnect 15 horsepower because we have a 10 horsepower and two 1.5 horsepowers. So that disconnect is 15 horsepower rating. And then feeding the compressor, we had 8 gauge. We had feeding each one of the starters. We had 14 gauge. And the branch circuit that's coming in and supplying to the disconnect and then coming into the air conditioning unit is actually 6 gauge. And that's kind of how we sized everything out with that. Hopefully that didn't confuse you at all. But just remember that, again, the smallest conductor we can use is 14 gauge. So that's how we established that for the fan conductors in our application. All right, so let's see here. What else would we want to look at here? Now, again, we used 430.250 to find our full load current. Okay, so that's how we did that. What else do we want to ask here? So code table 430.251b, assuming simultaneous ratings of all three motors and using the total locked rotor current of a 230 amperes, that was 40, 150, and 40 we saw earlier, shows a 15 horsepower as the required size. So that's how we came up with the 15 horsepower disconnect. Okay. Now, remind you, if motors do not start simultaneously, the compressor locked rotor current 150 amperes used with code table 430.251b gives a 10 horsepower rating. However, the higher of the two horsepower ratings must be used, hence the running currents impose the more severe requirements to dictate using a 15 horsepower switch, because worst case scenario is if all three of these were to come on, then that's what you need to have as far as the switch for the rating. Okay. All right. You want more information on that? You want to look at 440.22 for those requirements as well. All right. Look, that's generally all we're going to talk about in this episode in order to not make it overly confusing. I was just trying to give the idea of where we come up with the nameplate ratings. Again, at the end of the day, even if you have these motor systems that are going to combine all of these things together in its application, whereas you're going to have the condensing fan, the compressor, evaporator fan, and all this into one air conditioning unit, all of this information is going to be on the nameplate. So you kind of learned how you can size it, but at the end of the day, they're going to tell you on the nameplate, and it's just much easier to follow the nameplate. But now that you know how to do it, you kind of know how they came up with the method to the madness in order to be able to create that nameplate. But that's generally where you're going to be. You're going to be in part 3 and part 4 of Article 440, and that's going to be where you get all of the goodies that tell us how we're going to do that application. Okay? That's where you're going to be. All right? Now, the other thing that I will actually add, if I have separate circuits that are run to each motor of an AC unit, and this can happen. I've seen much larger units where they have a separate for the fan, compressor, and fan, let's say evaporator, fan, condenser, and compressor. All of that is 3 separate circuits. Okay? You have a separate one. Then that's different because I could have a 60 amp circuit breaker or fuse with a number 6 feeding a branch circuit panel, and then I could have a 15 amp going out to the fan, a 50 amp going to the compressor, and another 15 amp going to the actual evaporator fan, and I could have a 14 gauge, an 8 gauge, and a 14, 3 independent circuits running out to this one large air conditioning unit. That is doable, okay? And if that's the case, then I treat each one of these in 440.22 for the protection separately, okay? And that's how I would do that, and I would size it all accordingly, all right? So that's just another avenue, but more often than not, that's not what you run into. More often than not, you have one branch circuit that is under a 440.22B1, and you take the largest motor connected to the branch circuit plus the sum of the full load currents of the other motors. So that would be 175% times the compressor's current plus the sum of the fan currents. Okay, so if I was running one that way, okay, keep that in mind. Now, when it comes to the conductors from the starters, let's say, or integrated starters, that usually going to have overload device applications as well, then that's when you get into what's called the minimum circuits of the motor conductors. And that would be 125% of the motor's full load current, or 1/3, okay, remember what I was talking about earlier, or 1/3 the branch circuit capacity, whichever is larger, okay? So if, like we did in our example, it came out to be 7.5, well, that's not going to work because it has to be at least 1/3 the branch circuit's capacity, okay? So in our case, the branch circuit capacity that we were dealing with in our example was, I believe, let's see here, I can go back to my example, was a 50. Okay, so again, that was the 1/3 times the 50 where we dealt with that. So in our mind, we had to come up with what's minimum size we have to have. So that's where we came up with the 16.7 amperes or a 14 gauge because we only had the fan conductor was only 7.5 amperes. Okay, all right. Same concept if I did 1/3 of the 50 or 1/3 of the 60. Same concept, which would be, for in that case, would be 20 amperes. And under the 20 ampere application, just because people do sometimes get confused with that. Again, remembering where we're at and what our allowances are, then even that case, the 14 is good under the 75-degree column if everything's marked as such, nameplate such, taking into account 110.14C1, then 14 gauge under 75 degree would be okay for 20 amperes. Okay, so it wouldn't be a problem there as well. So just needing to know those applications is going to be very beneficial for you. But again, we couldn't do a 7.5 ampere conductor. We had to take whichever is the larger, so that's why we did it. And it has to be at least 1/3, like we said, 1/3 of the branch circuit rating. Okay? All right, so that's enough for that one. I think I kind of killed that one to death for you. Just remember, it's easier to follow the nameplate. You have some applications where you might have multiple motor compressors and multiple motors associated with it. Just take your time and follow through. Also visit our video that we do on motors, and we kind of talk about those different things. But you just simply go through and just remember, when you're dealing with these applications, take the nameplate. If you're dealing with a large group of these air compressed HVAC units, an AC unit that has integral motors, then the nameplate will take into account all of them. But you actually, if it has the ability to wire each of the motors independently, then you can treat the requirements of 440.33 and take that when you're dealing with the brand circuits. You get to take that into account. So hopefully you get something out of that, folks. That kind of is in a nutshell explains how we got the nameplate, and they're using part 3 and part 4 of Article 440 to come up with that value. Easiest thing you can do, folks, is just take the nameplates. Just read the nameplate. But again, I understand that there's some situations where the nameplate might have worn off and you want to know why they came up with the sizes. That's fine. Then I kind of gave you the general idea of how they do that. All right. Again, I just want to remind you, listen to all our podcasts on Spreaker, iTunes, Spotify, and now if you have Alexa, you can go into your skills and search for Master the NEC podcast, and you can get that as your daily briefing. So you get the most latest podcast from Master the NEC right there on your Alexa devices, like your Echo Spot, Echo Dot, or whatnot. Pretty neat. So thanks again. Until next time, folks, stay safe. God bless.
Every day, the future's getting closer. Every day, the future's looking bright. Every day is another beginning.